So apparently this happened, but life goes on. So here's what we're going to do, okay? Each day, I'm going to give a short presentation. I'm going to solve a problem or two, maybe give a little demonstration. Just make sure you have your notebook out so we can work on this and you can do it. You can rewind the tape, see how I did it. Okay, it's all available for you. You're going to get an assignment each day. It should take about 30 minutes of your time, sometimes a little bit longer, sometimes a little bit shorter. You'll submit this before next class and I will grade that as is. Okay. If you have any questions along the way, don't hesitate to email me. I'll try to respond to what you've got. And as time goes on, as we get used to this kind of distance learning thing, the lessons might change and evolve. I welcome your feedback as time passes. So that's where we're going to go with this. Today, we're going to talk about sound. And the reason we're going to talk about sound is we've been talking about waves. And so sound is going to travel as a wave. Now, if you recall, the velocity of a wave can be described by this equation, where the velocity equals the frequency of the wave times the wavelength, which we are going to represent using the letter lambda. So let's kind of look and try to visualize this a little bit. So let's create a sound wave. And right now it's propagating out. And I'm going to bring this puppy down here, and we're going to measure this, and we can see that, hey, we can represent this as a sine wave. But in reality, guys, let's try to take a look at this as actually particles, because that's why this wave propagates. The energy propagates, not the substance, not the medium itself. And you'll notice that specifically if we focus in on these red particles that have been identified here, those just vibrate and back and forth from an equilibrium position. The crests here represent areas of denser concentration. The areas that are rarefactions here are going to be represented by the trough. So this is the way I want you to visualize a sound wave propagating. We can increase the amplitude or we can decrease the amplitude. We can make it a little bit softer. We can make it a little bit louder. We can change the frequency a little bit. We can increase the frequency a little bit. Let's see how this actually sounds here. I'm going to put on this tone. And I can change this frequency. I can change it to a low frequency or to a higher frequency. Okay? And you can kind of see how that's going to be represented by these waves here. It's a little annoying. Let's turn that off. So the range of human hearing is actually in between 20 hertz or 20 vibrations per second up to 20,000 hertz. Okay? Anything above this would be, there are some animals that can hear off into this. Dogs can hear a little bit higher, specifically bats, dolphins can go way up on the high end. Some animals, such as elephants and whales, can hear below this level. Okay? So our range of human hearing can kind of fit into this entire experience. Now, the y-axis here is actually the intensity of that sound, and we're going to talk about that in a little bit. The x-axis represents the frequency. We're going from 20 hertz all the way up to 20,000 hertz. When you and I converse with each other, this is normally the range in terms of both the intensity and the frequency with which we are talking. Now, just to put a little frame of reference on it, middle C on a piano is about 256 hertz. That would be right in this area here. Doris Gruber ends up being about here, but our entire auditory experience is in this range right here. Now, the speed of sound in air can change based upon temperature because faster moving particles are going to happen when you get higher temperatures. And we can represent that using this equation. This is going to be a rarely used toolbox equation, one of those tools in the bucket that you're not going to use very often, but nevertheless, we're still going to use it. We're going to presume that the speed of sound in air at 0 degrees Celsius or 273 Kelvin is 331 meters per second. So if my temperature is higher than 273, this velocity of the sound wave in air is going to actually increase here. If it's lower than 273, it's going to decrease. Fairly straightforward formula, just the square root of the actual temperature divided by 273 Kelvin times 331. So let's look at a problem like that. Let's imagine we're out in the hot Arizona desert. Temperature reaches 319 Kelvin, which is about 114 degrees Fahrenheit. What's the speed of sound at this temperature? Very straightforward, guys. Temperature's 319. We're looking for the velocity. Here's our equation. All we're going to do is we're going to plug in the 319 Kelvin for that temperature, crunch the numbers. We're going to find out that the speed of sound of air on this day is 358 meters per second. Now, might not mean that much. Maybe if you are trying to create an echo, it's going to get back to you faster, but it will affect the speed of sound in air in musical instruments. So we're going to get to that in about a week or so. We'll talk about that. Now, the second thing I want to talk about today is something called the Doppler effect. Okay, let me play a little video here to represent that. Listen to the pitch of this fire engine as it approaches you, the bystander, and then as it recedes off into the distance behind your shoulder. Notice how that pitch changes as it passes you. It starts at a high frequency and then ends at a low frequency. Now, as it's approaching you, the frequency doesn't change, and then once it passes you, the frequency doesn't change. It's only during that shift as it's coming towards you and receding into the background that we hear that Doppler shift. So this is something called the Doppler effect. And the reason why the Doppler effect occurs is because of this idea. Let's imagine that this is a jet aircraft that's creating a sound. And let's imagine that this jet aircraft is stationary. If that's the case, the sound propagates out in all directions equally. Okay, it makes no difference if I'm here, 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 here. I'm going to hear that same frequency. But now let's say that I give this jet a little bit of a velocity, and I'm on this side. Now you'll see that even though the waves travel at the same speed, if I'm on this side, it's going to be a higher frequency and a shorter wavelength than if I'm on this side, even though the wave is traveling at the same speed. So as this jet passes you, I'm going to shift from a higher frequency to a lower frequency. So the equation for this is right here. The frequency that I'm going to observe is going to equal the frequency of the source sound times what's in parentheses here. The V here represents the velocity of the sound in air. Right here, this represents the observer's velocity. This right here represents the velocity of the source. Now, we're going to have to be very cautious about the sound, or about the signage here on these. So let's take a look at this, where O represents the observer, S represents the source, but we have to be cautious about our signage here. So you've got an ambulance that's traveling down the highway at 33.5 meters per second. It's emitting a frequency of 400 hertz. You've got a car traveling the same direction, but it's traveling at a slower speed. It's traveling at 24.6 meters per second. So this ambulance is going to approach this and then pass it and head off into the distance there. So what frequency does the driver of the car experience before getting past and after getting past? Let's assume the speed of sound of air, or speed of sound in the air this day, is 345 meters per second. So it's warmer than 0 Kelvin because not 0 Kelvin, 0 degrees Celsius. Because at 0 degrees Celsius, the speed would be 331 meters per second. It's normally taken kind of as a given that on a normal day at classroom temperature, it's about 343 or so. So here are our givens. The velocity of the sound in air is 345. The velocity of the source is 33.5 meters per second. The velocity of the observer is a negative 24.6. The source is approaching the observer. That's why we assign that a positive value. The observer is trying to get away from the source of sound, so we're going to give that a negative 24.6. The frequency that the ambulance is emitting is 400 hertz. So what is the frequency that is observed? Our equation that we're going to use is this. This is our toolbox equation. If I neglected to do so, make sure you label that as such here, that this is a toolbox equation for you. So what we have to figure out here is the signage. So I'm plus this velocity observer. The velocity of the observer is actually a negative value here. Okay? The velocity of the source, I'm subtracting a positive. So you see that both of these values are going to decrease, but the bottom is going to decrease more than the top. As a result, the frequency goes up, which makes a whole heck of a lot of sense here. Because the ambulance is approaching, the net result is that it's approaching, so the frequency is going to be higher. So once you crunch these numbers, the frequency that the car driver is going to hear is 411 hertz. But now let's presume that this ambulance passes while they're traveling in the same direction. Now, theoretically, the driver should pull off to the road and stop, but they're going to keep driving. They're going to do something a little illegal here. But so now, what I'm going to do is now the observer is actually approaching the source of sound, so that becomes a positive. But on the bottom, that ambulance is trying to get away. So this is going to be subtracting a negative. So if that's the case, both of these increase, but the bottom, the denominator, increases more. So as the ambulance recedes off into the distance, the frequency that you are going to hear as the observer of the car is going to be 391 hertz. So you have a lesson that is in the Google Classroom. Make sure you finish and submit for next time, and we'll see you then. Talk to you later.